presenting the topic of building a four-axis robotic arm environment. Actually, this is a topic I've wanted to work for a long time. So before I begin, I'd like to express my gratitude in advance. Mm, The content consists of six main topics, and we will go through each one in detail. The first thing uh, we will look at is the types of four-axis robotic arms. While there are various forms of robotic arms, the ones commonly used in the industrial sector can be categorized into three main types. And for instance, Delta robot, Scala robot, and articulated robot. Despite their difference in structure, they share one common feature. The gripper always faces downward because this design is primarily intended for the simple action of pick and place operations. Among these, I chose I chose the articulated manipulator, which I find the most interesting. With this robot, I plan to develop applications such as pick and place operations using object recognition with YOLO and a camera. Additionally, I aim to design the robot to support various end effectors. I also plan to build an effective control algorithm for the robotic arm using communication methods like TCP/IP or serial communication. If conditions error, I would like to take it a step further and work on a drawing project as well. Uh, this section is system configuration. The actuator is implemented using stepper motors and a photosensor is used for position zeroing to determine the current or rotational angle of the stepper motor. The MPU communicates with the general purpose computer via TCP/IP and exchange commands and feedback with the robotic arm through serial communication. Additionally, the system is designed to support various end effectors. Uh, this section is components about components. As I mentioned before, the drive components we will use stepper motors, specifically NEMA 17 and NEMA 8. The motor drivers will be DRV 8080 25. And the photosensor PM 45 will be used to correct the absolute position. The MPU has been selected as a Raspberry Pi, and the MCU has been chosen as a Raspberry Pi Pico. The other components used for the end effector have been categorized as follows. And the camera has been selected as a Raspberry Pi dedicated camera. The remaining parts will be manufactured using 3D printing. And this section is about software utilized. The reason I control the robotic arm through through an MCU instead of directly using the Raspberry Pi is first to reduce the load on the Raspberry Pi. Second, it makes a replacement easier in case the Raspberry Pi lacks performance or breaks down. Mm. Next is object recognition using YOLO. The reason for including this is to enable the robotic arm to move beyond manual operation or predefined algorithms and progress toward full automation. However, or thought about controlling a robot remotely from from a far distance or just imaging, it can give you a sense of accomplishing something extraordinary and handling advanced technology. That's ex- exactly what TCP/IP makes possible. The TCP/IP communication protocol is a network and internet-based communication technology that serves as a powerful tool for controlling robotics or remotely using a general purpose computer. For this reason, TCP/IP has been uh, included as one of the communication technologies to be implemented uh, in this project. Last is about hardware. This is the mechanism of the robot drive system. Before I choose, I mentioned about the articulated figure. This part is actually one of the most challenging sections to explain. First, all actuators except for those at the end of the manipulator are mounted on the robot's body. The reason for this design is to place the heaviest load-bearing components as low as possible, thereby reducing the robot's structure burden or burden of supporting its one weight. Next, let's focus on the red and blue quadrilateral quadrilateral uh, quadrilateral means is rectangular red and blue. Mm, Shapes are shown on the screen. To put it simply, when the actuators are in motion, this quadrilateral structure changes only the obtuse, uh, obs- obtuse and acute angles in eternally, maintaining horizontal stability. Thanks to this design, the end effector always faces downward, allowing it to perform repeat, repetitive tasks such as pick and place operations or with high stability. This structure plays a crucial role in improving the stability and operational efficiency of the robotic. Next is the end effector. Next is end effectors. Robots end effector can take various forms depending on the task, but for this project, we plan to implement a gripper and a vacuum-based pneumatic gripper. The gripper is used to physically grasp uh, objects or making it suitable for tasks that require precise movements. On the other hand, mm, the vacuum-based pneumatic gripper uses suction to lift or move objects, and it is particularly efficient for handling large flat items. Additionally, we are considering implementing a pen tool to enable the robotic arm to perform drawing tasks. This would equip the robot with multifunctional capabilities, allowing it to execute a variety of tasks. Such expansions will broaden the robot's application scope and enable it to take on more creative tasks. PCBs not only make circuit implementation more aesthetically uh, pleasing, but also help reduce size and prevent short circuits compared to manual soldering methods. This enhance both stability and efficiency. For this project, we plan to use KiCad, a widely used and free PCB design tool. Now, finally, as I conclude my presentation, please feel free to ask any questions, provide any constructive advice you may have. Thank you.